Okay, how's everyone doing? Moving along? Okay, well, thank you for your patience. I apologize for being tardy. Um, Hopefully, though, you've been able to get started on session 17. Just a couple of things. First, if um, you're preparing and thinking about exams and things for this semester, we have been assigned our time and place for the final. Okay, so it'll be on the 4th of May. And exam 2, though, is on the 7th of April. And so we will get to covering 2 more sessions that will be relevant. So Moore's circle for plane stress will be the last topic that we have for the exam. Okay, so the 31st is a Friday, and then we'll meet on our Tuesday on the 4th. Okay, and we'll talk about plane strain and Moore's circle. But this topic won't be on the exam. And then exam 2, you may bring a couple of sheets of notes. So you might want to bring the last sheet that you had for exam 1 along with another. Okay, any questions about these administrative details? Pretty straightforward, I think, at this point. So good. I guess on a more technical note for this session, focusing on plane stress, you've probably already gotten to take a look at some of the problems and notes on this. Just like to try to motivate it, because this topic with transformations is rather tedious, okay? As you've been able to tell, right? It's like free body diagrams gone berserk, okay? The reason, and I say this in the video, but kind of the reasons that we're doing this are, one, yes, to have the generic understanding of stress at a particular location and how orientation of an element at that location affects the stresses. And so that's nice to have understanding. That's great, right? But from a practical perspective, the reason we are interested in being able to understand how rotation of an element at a location affects our depiction of the state of stress is for figuring out whether or not we're going to have issues with failure, okay? Because we've already kind of talked about this a little bit, and we will definitely talk about it when we go through criteria for failure. Some materials are more susceptible to yielding and essentially breaking due to shear stress. Okay, so your ductile materials, you'll hear us we'll talk about that a lot. Okay, whereas the brittle materials like the ceramics and the glasses, those materials are more subject or more susceptible to failure due to normal stresses. So when you're given the combined loading or the state of stress at a particular location, it's not necessarily clear that that particular orientation is reflecting either the greatest values of shear stress that you might have or the greatest values of normal stress. Okay? And so what we're doing right now is developing tools that allow us to be able to essentially figure that out. Say, here's a state of stress. Is this the state of stress that's most concerning for failure or not? And if it's not, then we look and see, okay, what do we have to rotate by in order to see maximum shear stress or maximum normal stress? Okay? And we'll cover that in more detail in the future. Okay? I do suggest at least you have 2 problems that let you do the free body diagram method. Okay? So we have like a little bit better physical understanding for how to do these problems, but we're going to develop 3 other tools afterward. Okay, the general transformation equations, the tensor method, and then Moore's circle. Okay, so I suggest you use the free body method at least a couple of times. All right, and it is fair game for an exam. Okay, I haven't been that cruel to force people to do equilibrium on a slice during an exam. Okay, but it could, it's a possibility, so we should be able to do that. Okay, any questions so far? Thoughts, concerns? Okay, good, 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 good. You'll there are some great texts and videos out there on these stress transformations. So I like what the efficient engineer does many times, right? But it does a nice that's a nice job of depicting these stress transformations and plane stress. And then Roy Lance's page is quite nice as well in terms of depicting some of the mathematical transformations and things that we can do that way, either with tensors or other techniques. So we've got good resources and good videos, I think, out there on this particular topic, because it is a fairly how do you say, fundamental one for mechanical engineers. Okay, great. So I'll just go around if you have questions, and we'll be able to kind of go through things. If you have questions on previous assignments as well, we can talk about them too. Combine, right? This material is this is where we're in this is the hardcore part, right? And it is tricky. Step by step, it's okay, right? This is why certain YouTube people have so many views. We're not doing anything harder or less hard than anyone else, right? This is what is par for the course, okay? So step by step, breaking it down, we have the procedures, and I'd love to talk and discuss, individually with you as well, as you're getting these concepts. But this is pretty standard mechanical engineering, and even aerospace engineering. Or, as you might see, there are other courses that are very similar to this one in other departments, okay? Even here at Rutgers, because what we're covering is pretty fundamental to many aspects of engineering. How are you guys doing?
This is different than this one. We actually have to.
Oh yeah. Well, the notes, my notes are there, right?
Yeah, so we're using this.
Okay. Yeah. Yes. It's interesting why you say it's different, though.
I don't know. I'm not gonna do it.
Oh, okay. Well,
Yeah,
this is like crazy stuff, right? Yeah.
Too much all at once. We gotta watch videos now.
Sorry. You can watch other people's videos. I don't know. Okay. Right. That's why we put them up there. But I don't think some of these details they kind of gloss over. Which is fine. But if that's the other thing, if you guys find good videos that are that are really helpful, send them to me. I'll put them up for us to watch. Yeah, the questions are. Oh no, sorry, I didn't have. So yes, I didn't have time to put them on the website, but they're in campus. Yeah, so you go to campus. They're also on the instructional slides. So if you open the slides, they're right in there too. Yeah.
grabbing at the top.
Just
But that, this way
Okay, well, I'm sure some of you are working on problem 1, so if you've already done problem 1, you can ignore me. But if you're working on it, I thought maybe I'd just kind of go through it a little bit, okay, in terms of how you might approach this, okay? So this is a session Q1, all right? And so what are we asking for? We have a cylindrical pressure vessel. Okay, and maybe it looks something like this. And we've got an element there, okay? And it doesn't really matter where I pick this element, okay? As long, well, if it's on the caps, that would be awkward, okay? But as long as it's on the cylindrical skin, okay, it doesn't really matter. And we know that we have hoop stress kind of in that direction, and we often call that sigma 1, okay? And we have a longitudinal stress, that's sigma 2. So what I asked here is, what will the shear stress be if I rotate this element 45 degrees? Okay, and so if I come over here, and I'm just going to write it out this way, where I have a sigma 1 that I'm going to say is longer, and I have a sigma 2 that is shorter. Okay, and why is that? So sigma 1, right? That's the hoop stress. Sigma 1 is maybe I should do this the green. I don't know. Sigma 1 is equal to PR over T, and sigma 2 is equal to PR over 2T. And what we're getting at is we want to figure out what this tau x prime y prime is when we've rotated 45 degrees. Okay. Okay, and we'll call that theta for now. Okay, so any suggestions? What would you do here? Or what have you done? Make it 2 components. So this is the interesting thing. When we do these transformations, we actually want to, yes, we will get into like multiple components, but before we do that, what's kind of the process? We're doing this with equilibrium, right? So what we want to do is we want to draw the triangle, okay? And it can be a little bit tricky to figure out, okay, what the orientation should be for that triangle. In this case, all right, what I would do kind of an exaggerated form. Even though it says 45 degrees, I'm going to actually make it less than that so that I can make exaggerated triangles. Okay, that makes sense. So for example, so this, I would say, let's just kind of rotate it a little bit. Okay, maybe it's kind of like this, you know, like this, that's a theta, all right? And what is the triangle? What is this is the triangle that I can make that kind of helps me here? I'm gonna say it looks something like that, okay? And this face is kind of like coming down and showing that it's parallel, okay? And now what I'll say is that this is a sigma x prime, okay? That's the one I'm not actually interested in, okay? But it's relevant. And then the one that we are interested in is the tau x prime y prime. Okay. So because I made these kind of exaggerated, right? I'm trying to make this angle, it's not super great here, but this is like kind of shallow here, okay? I'm trying to make that less than 45. Which one of these, I have two options. Which one of these is less than 45 degrees? The top one, right? Okay, so I can then map over and call that the angle. I need a finer pen for this. Okay, in there. That's the angle. Now, when we're doing these, you don't, what's nice is once, because it gets a little messy, right? So you got to figure out where do I have to build and where do I not have to build. And once you have your x prime and your x prime y prime, or once you have your y prime and your x prime y prime, okay, you can pretty much leave those faces alone. Like you're not going to have to build up much, so that's fine. Okay, but the one thing we might want to add here, just, and it's almost as a technicality once you get used to this, is to say that there's some associated area. It's a small area, but that's the biggest of the areas of the three, okay, of the three faces of this triangle. And you know, when we say area, right, we're saying it has some really small infinitesimal depth into the page as well. So we've kind of mapped things out. We have a couple of options. I think the next thing I usually would do is say, okay, let me prescribe the areas of the two other faces. Okay, so the two other faces, right, are going to have this area, delta A, and this is sine, right? And this one is going to have a delta A. And I'll try not to get too messy here. Cosine. Okay? That's the adjacent one. Okay. So now the thing to do, which is what you were getting at, Amir, is that we want to be able to get the forces that we originally have onto this triangle. So to do that, we look at the original element, all right, and we recognize that the original orientation was such that this was, like the x direction, and this was the y direction. And we count ourselves fortunate that there are no shear stresses, okay? Because once there are shear stresses, it gets more complicated. So this is kind of a starter, right? Even though it has some variables and things in it. So here, the normal stress that we can draw, okay, we'll call it, well, we called it sigma 1 already, right up here. Okay, that's sigma 1. And then we'll call this other one down here sigma 2. And I can maybe make it a little shorter, but I don't really want to make it too short, because if I do, then I lose my ability to kind of keep track of things. Okay, so now I know this is acting on this face. I know sigma 2 is acting on the delta A sine theta face, but neither one of these, sigma 1 and sigma 2, are acting in either the sigma x prime direction or the tau x prime y prime direction. So we need to break these vectors into their components, treating sigma 1 as a hypotenuse and treating sigma 2 as a hypotenuse of a triangle that has two sides that are parallel to the other two sides that I'm interested in. Okay, so what do I do? I've purposely, again, this is one of the beauties of making data exaggerated, is that I can kind of also exaggerate this. So I'm going to say that's kind of like that, and that's kind of like that. Okay, and then I put the arrows in to make sure I know which direction I'm going. Okay, so this plus this vector, this adjacent plus this opposite, right, get me the hypotenuse. And so I know that this angle this angle is, again, once again, it's theta inside here. Similarly, I can draw something that's kind of parallel to the tau x prime y prime, right? And kind of parallel to the sigma x prime, the x prime direction. Okay, and so this one has this angle theta. Right. So what do we do at this point? We're now pretty much in a position where we can start to do equilibrium. Okay, and so for that, let's say we actually don't need to do equilibrium in the x prime direction. We need to do equilibrium in the y prime direction. All right. So y prime, I probably should have drawn it up here. Y prime is this direction. X prime is that direction. Okay. So sigma f y prime equal to 0. What do we have? What do you want to start with? Well, what do you normally start with? Suggestions? There's not really. Yeah, Michael. Yeah, that's how I would normally start. I would do tau x prime y prime times delta A on this face, right? Which gives us a force associated with the x prime y prime, the tau x prime y prime. Okay, and now from here, usually I go ahead and I pick a face, and then I look at the forces I have on that face, right? So here, let's just go to the delta A cosine theta face, this one. I have a sigma 1, and if I need it to be, I need a component that's acting in the x or the y prime direction, right? This direction. It's going to be this little sliver out here. And that is going to be a sine, right? Sine of this angle here. So, and is it going to add or subtract? Well, the arrow is going in the same direction as tau x prime y prime. So now we can say that this is going to add. And it's acting on the delta A cosine face. Like that. Okay. What do we do with this one down here? With sigma 2? All right, because, well, there are no more forces, right? This one is acting, you know, you ask yourself, what's going on with this one? Well, this is orthogonal to the y prime direction. So this portion, the adjacent of this hypotenuse for sigma 1, has no contributing effect, right? Down here, again, we're looking for something that's parallel to y prime. And what do we see? We see we have this component right here, the adjacent. So that's going to be a cosine, right? And it's going down, it's actually in the opposite direction, right, of the y prime direction. So now what we'll have is a minus, and it's adjacent, so cosine theta delta A on the sine face is equal to 0. Okay. So now I can write that this is equal to minus sigma 1 sine theta cosine theta plus sigma 2 cosine theta sine theta. All right, just doing the algebra. And I don't really need a calculator here because what is theta is equal to 45 degrees. All right, so theta is 45 degrees. That's the rotation. So sine of 45 and cosine of 45 are the same in this, you know, in it, so that's nice. So we get minus sigma 1 square root of 2 over 2 square root of 2 over 2 plus sigma 2 square root of 2 over 2 square root of, oops, that square root was too big. Like that, okay? And I know that sigma 1 is PR over T, okay? So I have now a PR minus PR over T times 1/2. And then over here we have, all right, we have PR over 2T. So we have PR over 2T times 1/2, okay? So this ends up being equal to minus PR over 4T, okay? And we want the magnitude, right? So the magnitude is what I asked for, because it turns out, right, if you picked your sigma 2 to be your x direction and your sigma 1 to be your y direction, which is not what I did here, right? Then you won't get the same sign, okay? So that's the answer then. Well, it's actually the magnitude of this, right, is equal to PR 14. Okay. So maybe as we're going, we have a few minutes left, but we can. I don't know if anyone wants to do an example. I mean, they're on the notes, but if anyone wants to do an example that has shear stress, right, that's a little more complicated. But I'll let you guys go. I'll just go around and we'll talk.
You guys are rocking. Rocking?
Yeah. Or Brandon. Yeah.
One of these days, you wouldn't make tomorrow. So I get confused. Seriously, that's why you're using that.
Okay, I'm looking at the, and if you can ignore me, I'm sorry if I'm being annoying, but maybe I should, it looks like there's lots of questions on number 3 for the last homework assignment. So I guess this is going back. I don't know, I will just do it this way. Okay. So we have a cylinder. And we're saying that this T-app, well, let's see, let's look our location. Okay, it's the most positive Y. All right, so it's kind of up here at the top. And we have our directions, Y. We have X coming out. Okay, and we have our C as the radius. Okay, and there's a direction of force being applied, P. Okay, and this is in the negative Z direction, right, from the right-hand rule. And we have a T-app, right? So T-app like this. Okay. And so the question is, let's find tau xz, okay, at the location. So I think there are a couple ways to look at this, but one is let's first draw what tau xz would look like. Okay, so at the top, right? So now if I draw A, that's A. I'm going to say this is the left side, right? So this is, I'm going to say this is X. Okay, so this side here, this side over here is going to be this left side over here. Okay. And we are going to do this? Okay, well, let me see, I might have done this wrong. This is Z, all right? That's the upward direction there, okay? And we can see that there is going to be a torque, right? That's going to be kind of twisting it this direction, like this. Okay, from the T-app. All right, so this T-app, so I've got one component, right, that is going to be at least the way this is drawn, okay? It's going to be like this. And this, so we can say this is the tau. It's kind of like it's like a tau, but it's like a negative xz, all right? Like that. So this is just equal to the T-app C over J. Okay. And the other component that will be interesting, okay, is the transverse shear stress. Okay, so what's happening with transverse shear stress? Let's go ahead and we'll draw for this. I think it's useful to draw the circle. Here's our point A, okay, and this is Y, okay, this is Z, and then coming out is X. The transverse shear stress, right, is going in this direction, right, P, like that. So the transverse shear stress that is being applied to this system, okay, at least the way we're looking at it, okay, is going to be thought of as acting on the neutral axis here, right? And I'm going to say it's going in that direction. Okay, it's going in the same direction as P. So what I think about is I think about stress. All these stresses acting in that direction. Okay, and since this is a cylinder, okay, the actual, so P av is just P over A, tau av, okay, but the T from what we call V, all right, this is 4/3 times tau average. So this element, all right, if I look at it, right, and this is, so this is now with Z facing that direction, right, that's going to be going in the opposite direction, right, of what I have here, right? So this is X coming out, right, and then it's going in the opposite direction. So what we can write is that we have tau xz is going to be equal to this minus tap C over J, but plus the 4/3 P over pi C squared. Yeah. And that's it. Okay. If you have questions, feel free to let me know on that as well. Okay. Good. I think we're at time. So thank you everybody for being here, and have a wonderful afternoon.